Okay, yeah. The second topic for today is just give you some background about Monte Carlo approximation and give you some extra exercise or examples to see how Monte Carlo approximation can be useful. So actually, Monte Carlo approximation, we can use it based on certain theoretical results. Okay. So suppose we want to summarize posterior distribution of a function of theta. So notice that I start to work with a function. Right now, like so far, I would say we're working with just the unknown parameter. But what if we want to work with functions with it? Okay. So Monte Carlo approximation can actually help us get there as well. So generically, I'm trying to look at a parameter phi, which is g theta. Okay, so theta is still the parameter in the model. We have seen how you can summarize it through Monte Carlo approximation, right? If I know it's a normal, I generate a bunch of normal. If I know it's beta, I generate a bunch of beta. And in the example that we just did, if I know it's gamma, I'm going to generate a bunch of gamma and summarize it. Okay? But sometimes you might want to know certain functions about it. Then you can compute the expectation through change of variable. Okay, so I put the form here for you. And we know that if we don't know how to compute the integral, then we are able to use the approximation technique, and in particular the Monte Carlo. So let me just show you some of the details here. We already worked with, I think, how to get it before, like you just generate a large number of draws, right? And then we take the mean. That will be a good approximation to the actual mean. So that's why based on law of large numbers, if I have a large number of draws from its posterior distribution. So this is our typical notation of posterior here. We are taking S values of the posterior of theta, right? So we get a large number of them, like 1,000. And then based on a law of large numbers, if we take the average of the draws that we get, it's going to be approximating the actual mean. Okay, so that's what this form is about. The theoretical mean on the left-hand side will be approximated by the sample mean. Okay, again, the sample mean is different from what we usually talk about, that we get a sample and take the mean. This is, we get a large number of samples from the Monte Carlo and then take the mean to approximate it. Okay? So that's for just the parameter theta itself. If you're curious about function of theta, then you can do something very similar. So the left-hand side is looking at the theoretical expectation of the function of theta, the posterior of it. And you can also just take a large number of draws. Now, remember, you take theta, but then you also apply the function here. Okay? So the sample mean is going to converge to the expectations if you have large enough S. So that's why I think maybe was it in lab 1 or lab 2, at least in lab 2, I think, we were using approximation as well as the exact solution, right? And I asked you to evaluate if they're close enough. So sometimes if your S, I think most of the examples we used in class, S is 1,000. I think overall will give you a good approximation. But sometimes later on in the semester, you might see that we want to get even larger number of draws to get a better approximation. Okay. So the accuracy, I would say, depends on the value of S. For now, like 1,000 should be good. And that's why, like, say, you generate like a vector, remember, like R gamma or R norm, and then you have a bunch of draws, and then you just take the mean of that vector, and then that will be the answer of your Monte Carlo approximation to the mean. So this is what we already did, but today I just want to cover that if you work with functions of the unknown parameter, you can do that as well. And sometimes that's actually a desire to do. So one last thing, I will show you the examples of why sometimes we want to work with functions in a minute, but also just so you know that, so this was the draws that we take, right? These are from the posterior distribution. And remember, sometimes we also just say, what would be a good example? I think we did at some point, that say, if you get a bunch of draws, oh yes, well, we're trying to come up with like the 95% credible interval, that kind of stuff through simulation. Remember, we get a large number of draws, and then we use the quantile function of the draws, at particular two cutoff points, right? If I want a middle 95% credible interval, I'm going to do the left 0.025, right? On the right, I will do 0.975. And that's based on this particular result, that you are able to approximate the empirical CDF using approximation as well. Okay. So what this is saying is that I'm looking at a cutoff point C. Okay. And I can approximate that particular, I guess at that point, quantile by just counting how many draws that have is smaller or equals to C. Okay. And then I count. So this form, I don't know if you know this notation, is cardinality. I'm counting how many observations are, like say in this case, theta S less than C. So I count how many there are. I divide it by the total number of draws that I have. I will get a percentage. Okay. So that will give you a good approximation for the quantile. And that's what we actually did using the quantile function. Okay. So that's just another justification. And of course, if you're working with functions of C, okay, so another type, I would say this should be S. I'll correct it later. And you can also approximate it using the same idea. Okay. So there's some background. We already do most of it, just not yet about the functions. And today I want to cover that so you know why we're doing this and why we can do this. All right, so just to put it in practice, we saw it before that we have this beta prior for the proportion, and then we're gonna, for the Tokyo Express dining preference example, and remember we come to this posterior distribution, okay? So it's beta 15.06 and 10.56. And remember, we did the exact solution using either the beta interval or the Q beta function. Okay. And that will be able to give you a middle 95 in this case. Yeah, middle 95% credible interval. Okay. That's when you know exactly what the posterior distribution is, right? And through simulation, what we did, remember, is we use our beta to generate S number of draws, right? And then we use this quantile function to look at these two cutoff points. Okay? And the reason why we can do this was from the previous slide, that we are able to approximate those quantiles by counting, like you sort them out, like you sort them from the smallest to the largest, and you put like two cutoff points and then try to find those points. Okay, so you see that overall, with 1,000 draws, the approximation is pretty good. And if you go even further, like larger value of S, I think it will give even better results. Okay, but with this kind of approximation accuracy, I think it's pretty good already. So 1,000 right now is definitely sufficient. Okay, make sense? All right, so let's cover a couple of functions of theta, like why, like when would you ever work with functions of theta? For the proportion case, actually, we know that P is the success probability in this case. And another definition or another terminology is the odds. You probably have heard about this before. I mean, in daily life, I think people just use odds as probability. But the right terminology of that is actually the ratio of the success probability over the failure probability. Okay, that's the academic definition. So that's why O, we use that for odds, is a function of the unknown parameter. Okay. So if I have a lot of idea, like say I know the posterior distribution for P right now, I mean just now we did it, it's going to be some beta distribution. And we know that we can summarize like doing Monte Carlo approximation, generate a large number of draws about P and then make inference about P. But now if I ask you, okay, I want to know about O, which is defined to be P over 1 over P, then how can I make inference about it? Okay, so this is the case that O is P over 1 minus P, and that's the example of a function. So you see that O is a function of P, P is the unknown parameter, and now we're doing inference about this function. Okay, so earlier we covered that regardless of what kind of functions you work with, you should be able to use Monte Carlo approximation as well. So I'm just going to cover the example. So before we get there, well, you can always try to work with the exact solution. And this is another good example of the change of variable, the transformation of variable that we reviewed before. Right? Remember, we have to check the function is what, monotonic and differentiable, and then we can apply that formula to do change of variable, right? So if you do that, that will be able to give you exact solution. And you can see that the form is a bit crazy over here. And so typically we don't work with this exact solution because we now know that Monte Carlo approximation can easily get that for us. So you see what I'm doing here? We're still setting S to be 1,000 here. And remember, we just use like beta samples just to store all of the values of P, the draws of P, right? And what I simply do is I just apply the function of Oz directly on the draws. Okay? So this is a vector, right? It's a vector of length 1,000 because I make 1,000 draws from this beta 15.06 and then 10.56. And what I do is for each, so again, R operates vector, element by element. So this line is doing for each beta draw that I have for the P, I'm taking its odds. Okay, I'm taking P over 1 minus P. So by doing this line, I'm having a vector again of length 1,000, and each of them is a draw of the odds. Okay, so this is done in a sequential way that I know about my P. I know it is a beta posterior distribution, so I'm going to go with drawing it from this R beta. But if my interest is not about the probability itself, it's about the odds, then I can use directly using this function G over P, which is P over 1 over P, sorry, P over 1 minus P, and then that can give me a sequence of draws of the odds itself, and then I can summarize it. Okay, yeah, so doing action, you see that I can return the mean. Right, this is, again, is approximation, right? We have a bunch of draws, and you can summarize its mean, summarize its median, summarize its quantile to give you a middle 95% in this case as well. So all of this are based on the theoretical result that we covered briefly just now. And so I want to show you that not only you can work with the unknown parameter P directly, but any kind of function of P, you can work with using the Monte Carlo approximation as well. Okay, so Oz is the most obvious example to give here. Okay, but suppose in the normal, remember in the normal model that we covered before. So remember, we work with mu and sigma, right? Suppose, let's see, I think if we suppose this was known and this was unknown, then we were using conjugate prior of 1 over sigma squared to be gamma, right? And then we derive the posterior to be some like another gamma. And suppose that I don't want to know about 1 over sigma squared, okay? I want to know just about sigma, right? If that's what you want to do, you can, so let's see. The posterior is what? Anybody remember what it is? I probably don't. The posterior of 1 over sigma squared is gamma A and B what? Anybody? One of the term will add sum of the yi, I think. Oh no, sum of the I think it's a gamma.
A plus n over 2.
A plus, oh yes, n over 2.
B plus
1
over
over, right, it's the sum of the square. Yeah.
Thank you so much.
So this is the posterior, right? Yeah. So this is saying that if I want to draw this P, which we define to be precision, then I can just use R gamma, right? I generate a bunch of them. But what if I don't want to make inference about P? I want to know about sigma. So what you do, first step, you generate phi, right? You can get a large, like a sequence of them. And the second is you would just take those draws, like take 1 over phi, and then square root of that will give you the sigma, right? So if I ever want to summarize sigma instead of phi, then Monte Carlo approximation, applying the function on top of the draws that you already have, will do the trick. Okay. So yes, go ahead.
Oh, sorry. I was just gonna ask. I think I'm just a little like. Can you remind what you mean when you say conjugate prior? Like what exactly we're referring to there?
Sure. Yeah. So conjugate prior, by definition, is if you have a conjugate prior, then you start with a prior distribution from a given family, like beta or gamma or normal, and family of distribution. Your posterior distribution once you derive it, it comes from the same family. Okay, so from the same family. So this, I think, is related to Josh's question earlier as well, that earlier I think Josh was giving the example, okay, I'm gonna start with the beta prior for the Poisson rate, right? So Poisson has the only parameter theta. I'm trying to give theta a beta prior. So if you derive it, looking at theta, it's not going to be something that you are able to recognize. Okay, so that will be an example of non-conjugate prior. Okay, but examples of conjugate prior that we have done so far. The first one is beta binomial. So we typically, you can just say, in this case, use a hyphen to connect this to. Before the hyphen will just be the prior distribution. Okay? After the hyphen, it's just the likelihood function. Okay? So beta binomial was the derivation that we did in the previous chapter, right? That we saw that from a beta prior for the success probability in the binomial likelihood, you're going to come to a beta posterior. So that's a conjugate. Okay. What about the other one? Anything else?
Gamma normal.
Gamma normal. And gamma normal is specifically on the precision parameter of the normal. Okay, so we need to be super careful about saying what is the parameter. So gamma normal is for precision. Okay. And I would just add this here for success probability.
So it's not like we like know certain functions will always be conjugates, but you're just like this will be conjugate, and then we prove it's conjugate. Okay.
Yeah. So right. So the thing is, I guess unless you try to show it, otherwise you will never know which one is conjugate or not. And what I can tell is, like what Josh said earlier, that won't be a conjugate case. Okay? I mean, just in your mind, if you think about it, like the terms wouldn't come together to be anything that you know. So right. And one more example, I think, is the normal, right? And that's for the mean, okay? That is the case where we assume that the normal, so there are two normals here. The first one is the prior, the second one is the likelihood, okay? And this is the case that we assume that the standard deviation is known, right? We only work with the unknown mean, and then that's another conjugate prior, okay? Anything else?
Gamma Poisson that we just
The gamma Poisson that we just covered. Okay. So if we try to summarize, I think this is all we have seen so far. Okay. Yeah. So yeah, go through the definition, go through the derivation, and then hopefully you can register the idea about conjugate prior. And we sometimes call it conjugacy. But like we were talking about earlier as well, that conjugate prior is easy to work with because the form is nice. But at the end of the day, if you come up with other prior distribution that you prefer that can reflect your beliefs better, then don't even worry about conjugacy. Because later we're going to learn about other approximation methods to the posterior. So conjugacy is nice because we know exactly what the posterior distribution is. So you can either use exact solution or approximation. And we try to see from both sides, and you can see that if your approximation is good enough, like large enough number of s, like value of s, you will get a really good approximation. But from now, like from next unit, you will see that, well, conjugate prior might not exist. And then there are still other ways that we can deal with it. Great, I think, yeah, that's talking about conjugate prior. So yeah, finally, I guess we get the chance to define it properly. And down here, I think I was just giving the example of, well, if I want to know about sigma but not phi, I can generate a bunch of values of phi from its posterior gamma distribution, and then just do the transformation on the draws that I have. And the function is directly being applied to the draws. Okay? So we can summarize that. Maybe that's what I asked in that too. I don't remember, but again, there are fundamental. I mean, there are things. I mean, there are theoretical results to back this up, and that's what we're covering today. Okay. Anything else? Okay. All right.
Distributions are considered the same family.
Yeah. So pretty much, yeah. Whenever we say same family distribution is the same distribution, but different parameters, of course. Like you start with beta AB, but you come to beta, well, A something and then B something. It's something different. Yeah, so they are both from the same family of distribution, but they're different. Okay. All right, so this is a Monte Carlo approximation to the up. And one last thing I want to cover is sometimes, so this is still in the field of doing proportions, okay? But sometimes you might compare two proportions, okay? And the example here, suppose we get data from VA hospitals. For each year, observe N patients and Y, the number of cases. And we just loosely define this for now as real failures of particular outcome. So let's say the observed data, as we know, is you will have Y1, N1 for 1 year, in this case 1992, and then Y2, N2 for another year, 1993. Okay, so let's suppose now we observe this and we want to see if the, like say the number of cases, or I should say the proportion of the cases has been improved. Okay, so this will be the case that I'm looking at one hospital and I observe data from 2 consecutive years and I want to make inference about the proportion comparison. Okay. So if that's the goal, you might just gonna give independent binomial distribution, right? You're gonna use, because this is like outcomes and then thinking about proportions. So if we're gonna go with P1 and P2, P1 for 1992 and then P2 for 1993. So the question will be, has the probability changed or like decreased in this case, preferably, between these 2 years? Okay. So, well, this is open-ended question. We do have some ways through Monte Carlo approximation to solve this. But before we get there, I just want you to talk to your neighbor really quick, just to think about what you would do. I already tell you that, well, we can get independent binomial model. And we have 2 sets of observations. Each has the number of trials, right? And then the number of successes. So how can I set up my model? The likelihood, the prior, et cetera, how would you do that? So open-ended, talk to your neighbor, and we're gonna look at it together in a minute. Okay, let's hear from some of your ideas. Any idea how to compare? Well, I think the title is compare distribution. So what are the things that we're trying to compare to? We're trying to compare, I guess, P1 and P2. Okay. So how can we set this up? I think there's the likelihood both of them are binomial, right? Because for each of the years is a success count out of the number of 12. So naturally, we would choose binomial model there, right? If we do that for P1 for 1992, that might be, if you want to use the conjugate prior, you can use beta binomial like we covered, right? For 1993 as well. So how can I put priors for P1 and P2? If we try to use the beta binomial scheme that we covered before.
Would you want to use the same prior for both of them and see how the posteriors differ?
Good point. So if we give the same prior, so of course we have to have two priors, right? One for 1992 and the other for 1993. And so the question is, do we want to give the same prior to see how they are different in the posterior? What do you all think?
No. I think no. I think you would want to use one prior, say like betas, whatever, and then update that prior with the outcome of experiment 1, and then update that again with the experiment 2 and see how different your first posterior is from the second one.
So that's another idea. Zach's idea is that, well, it is pretty special in this case because it's 2 consecutive years, right? Yeah, so, well, like the suggested model is you have independent binomial, but sometimes you might argue that no, we should not do independent, right? They might be linked. And same goes for the prior, right? And they can be independent, but the thing is they can be the same prior but still independent. Yeah, so they're like small differences here. So the different ways to do it, so let me just cover the one that I prepared, and we can discuss, the ones that you might have in mind, and then how to do it to be correct. So I'm just covering the situation that you can actually give independent, continuous, uniform priors. If you don't know anything about it, just put it uniform. And remember, we want to work with conjugate, and we covered that a uniform 0,1 is actually a beta 1,1. They're equivalent. Okay, so from uniform 0,1, you can go to beta 1,1. And if you do that, and we're giving independent prior to the 2 years, you can just treat them whole separate, right? I work with the data and the prior for 1992, and I work with the data and prior for 1993. So I'm going to count to 2 different posterior distributions, okay? So I'm just going to give you the results here. This is just like the conjugate prior that we covered before, how you're going to from a beta prior to the beta posterior. Okay, I plug in the numbers for you now, so you can see that P1 posterior of it is beta 307, 346, and P2 is 301 and 406. Okay, and one more thing here, it's pretty important, and I think some of you are already talking about it, it's about the independence. Okay, so we assume independent priors for now, and we also assume independent data model, so the posterior are going to be independent as well. If you ever want to show it mathematically, you can write out the joint, like of the posterior, and you can see that they naturally break into 2 groups. Okay, one is about P1, I think. The other one is about P2, and each of them is a beta posterior. Okay, they don't interfere at all. Okay, but you can also argue that from independent priors combined with independent likelihood, I will go to independent posterior. Okay, so if you have that in mind, then what you can do is, well, I can just generate a bunch of draws from this, the first beta posterior, 307 and 346, right? And I have a bunch of draws about P1, which is posterior draws. I can also do a sequence of numbers, draws from the second posterior, and then I just compare them. Okay, so this is another example of doing Monte Carlo approximation. You can think of them as functions on P1 and P2. Okay, so we know it's P1 and P2 to start with. You can summarize P1, P2 independently, that's fine. But if our curiosity and interest is about comparing them, you can think of it as a function. And I should mention, you can actually define it just to be this delta that I put on the top. It's looking at the difference between P2 and P1. Okay, so this is a function. Think of it as a function, but now we do have 2 parameters here that can be a little bit different from before, because before, remember, the odds is only applied to one of the parameters, right, P. Now we have P2 and P1. So you can, if you want, but pretty messy in terms of from the frequent distance method, how you can prove that you are able to do a transformation to get the particular distribution of the difference, which is delta, but that's not our focus. What you can do is you can actually just generate a bunch of draws. So I'm doing 5,000 just for demonstration. And you can see that I put in the values of y1, y2, n1, and n2, right? And then I can generate, so I'm using t here. T1 is the vector looking at all of the P1 draws. And this is for 2. And what I do is I simply take the difference element by element, and then I'm counting how many of them are smaller than 0, and then I divide it by the number of simulation draws that I do. Right? So this is another technique of Monte Carlo approximation. Remember that if you want to look at, like, compare certain things, in this case, we just want to see if the value of D is smaller than 0 or not. And then you can just sum that logical operation and then divide it by capital S. Okay, so that will give you a percentage. Okay, it's going to give you a percentage approximation to the true percentage of P1 to be, I guess in this case, smaller than P2, right? Oh, no, I think, maybe I got it reversed a little bit. Sorry, so T1 is for P2, I think, right? Based on the definition I have over here. And T2 is about P1. So T1 minus, okay, so this is trying to approximate P2 minus P1, right? So this is summarizing that delta. So earlier, if you remember, I did define P2 minus P1 to be delta. So I will have, yeah, so I think it's still correct. It's a little bit awkward that I think I defined T1 and T2 sort of reversed. But I think it's still giving us the approximation probability that delta will be smaller than 0. Okay. So this is just another example of doing Monte Carlo approximation. You can be pretty creative if you want to work with multiple things, in this case, 2 different models. And then I want to compare the two parameters from 2 different models, and then you can do this crude comparison in some sense. But Monte Carlo approximation will still give you a pretty good approximation in that sense. Okay. Yeah. So in fact, if you've taken other like stats courses in the past, I mean, comparing to proportions and comparing to means, those are pretty typical like tasks, right? So in frequent distance method, what you do is you have to derive, or like you're given the distribution of the difference, right? Like usually it's a normal approximation, and you have to like compute the mean and the standard deviation of that, and then you like use the Z table, whatever, and you can get that particular comparison. So Bayesian methods, as you can see, the computing is pretty important and pretty handy as well. That I can always generate draws and then use computation power to approximate my result. Okay, a Monte Carlo approximation is one of the pretty important techniques in this field. Okay, anything else? I mean, that's all I prepared, so the rest of the time can be used for lab 2, and I can just walk around answering questions. And yeah, because starting from next week, we're going to start the new chapter on Gibbs Stanford and MCMC. So that would be the case that posterior concave posterior is not available. What we need more.
So they're like,
Yeah.
is it